Good afternoon, everyone. Welcome to the problem solving session of design of reinforced concrete structures, week 6. So, our session is scheduled from 3 to 4 p.m. In 1 hour, we will be looking at some design problems on the design of slabs. You would have gone through the lectures given in week 6 and week 5 because already there are lectures on design of slabs, one-way slabs and two-way slabs as well. After the design of shear, they have directly come on the design of slabs. So we will be also solving some problems related to one-way action of slabs, one-way design of slabs, and later on the next week we will also shift to the design of two-way slabs. So for the design of slabs, we will have a little bit look into what slabs are and what is one-way action and two-way action for the design of slabs. And in today's session, we will be primarily dealing with a design of slab, one-way slab. So let me start. So, what slabs actually are? So we can say that slabs are actually the floor systems that resist the gravity loads. These gravity loads can be either dead loads or live loads acting on it, and these loads are then directly transmitted to the vertical framing systems that ultimately transfer those loads to the ground. For example, if we have this load bearing system like these columns, we have a slab over them. What this slab does, this slab transmits all the live and dead loads that are acting on it to the supporting columns, and these then columns transport it to the foundation or the below column that will be on the below story or the and the all the loads and below story and then to the foundation as well. And these actually in technical language we say these slabs as diaphragms. These slabs are actually diaphragms and they help in also maintaining the stiffness of our structure. Due to the high in-plane stiffness of these slabs, they give very much rigidity or stiffness to our structure when it is subjected to transverse loads. For example, weight load or earthquake load when it acts on our structure, due to the high in-plane stiffness of this slab system, it plays a very important role in stiffening our various vertical frame elements. So, in the first lectures of the week, first I have already given you the types of various floor systems. But from the design point of view, there are only two basic types of the slab systems, which are one-way slab system and two-way slab systems. So, let us discuss what is one-way slab action and two-way slab action. For example, this is our slab panel. This is our slab panel. If this is its x dimension or the longer dimension Lx, and its vertical dimension or the shorter dimension, it's Ly, and it is only simply supported on the two sides. Simply support on two sides. We say that this when the gravity loads, either it will be live load or the dead load of the floor system itself. Dead load may include the finish and other things and the material inside it. If the dimension of this slab system is such that Lx longer dimension divided by the shorter dimension Ly is greater than 2, then we will treat this slab system as one-way slab system. What happens in this one-way slab system is that this slab system will bend or have deflection predominantly in only one direction. It will bend like this. For example, it was supported on simply support on walls in two directions. It will have a primary bending in only one direction. Whereas in case of two-way slabs, we can see that same if it was two-way slab having dimensions like this, it was having Lx like this and Ly like this. X dimension and Y dimension. If longer dimension divided by the shorter dimension is less than 2, this ratio, then this slab will have predominantly will have two deflections in two directions. I can say you like this. For example, it will if it was like this, it will bend like this. In one direction, it will bend like this, the longer direction, and in another direction, it will have also some deflection like this. You can consider it like a plate. uh, Make it more enlarged. You can say like this. If it was the same slab, look, it's having two deflections. Nah? If it was the original profile of the slab, it is having two deflections, one in this direction and another in this direction. These two directions. So when the slab bends in two directions, or it is aspect ratio is less than 2, we can say that it's a two-way slab action. Aspect ratio. Now we can see in one-way slab action, for example, if it was one-way slab action, we can have bending moment variation in only one direction. We have predominant bending moments will come in only this direction, like this. Right. Well, in case of two-way slab, we had bending moments, transverse bending moments coming in two directions, which were of significant value. We would have it in two directions like this. First variation like this, another variation would have come like from this side, as it's a two-way action, like this. So for timing, we will have this main to we will have to differentiate these two slab systems on this aspect ratio. If the aspect ratio is greater than 2, we will have one slab action, and the slab will predominantly bend in one direction. If we have aspect ratio less than 2, we will have the direction of the bending in two directions. These two-way slab systems will be studied in further weeks, and later we will solve the problem on these two-way slab systems as well. For example, if we have, there is one more point adding to this fact that one-way and two-way slab systems. If this one slab system is supported only on two opposite sections, then it will be one-way slab action always. No matter what will be the aspect ratio, it will bend in predominantly one direction, and it will bend in the direction in which it is not having the support. But when it comes to the two-way slab action, if we alter the loading or the support conditions, for example, we allow the support conditions on all the four sides, we will have uh, two-way slab action will come into play, and we will have to also look into the aspect ratio as well. So when you alter the boundary conditions, you get the two-way slab action into picture. So now comes to one, we will shift to our focus to one-way slabs. So this one-way slab, how can first we have to see how can we design this one-way slab. This is a huge plate like structure. How can we design this plate for we have to design it for the reinforcement, we have to design the spacing, detailing, uh, main reinforcement, distribution reinforcement. How can we design it for the whole structure? It will take a lot of time, but there is a smarter way of doing it. Well, what we do for our slab system is that, for example, if it was a large slab system like this, it is like this. It's extending on all the sides. I am cutting one part of it from the main element. This mark shows it's continuous in this way, it's continuous in this way, it's continuous on. We can have this slab system as a if it is one way action in this direction. For example, if this slab system only bends in this direction, this primary direction, we can cut these slabs as, we can treat these as small beams, each of it 1 meter, 1 meter, 1 meter. We can divide these whole slab system in a number of beams placed side by side to each other, and they form a slab system if it is only one way slab action, so that we can cut one beam from it like this. We can have this beam, this one, like this. We get a beam section like this. We have a width 1 meter, and depth will be the gross depth of this slab, gross depth D. We will get a slab section, beam section like this, gross depth D. We can analyze, we have already studied the design methods for the design of singly reinforced or doubly reinforced beams. We can easily design this beam section, and we can have the design for the whole slab system. If we are able to find the reinforcement to be placed at the bottom side, or the tension reinforcement, that will be the equally reinforcement for this slab section. We will have then reinforcement like this. We will have the reinforcement like this, and there will be another reinforcement that we will provide, that's also known as distributive reinforcement. So this reinforcement will be mainly because I have cut this slab section from the main part. It will be having the moments like this. Everybody agrees with this fact that it will be having moments like this. So the reinforcement that is provided at the bottom of this slab that I designed from the beam section, it's known as primary reinforcement. And the main, anything you can reinforcement. It is majorly responsible for taking these transverse moments on our slab section, or the main loading that comes on our slab section, because that loading is responsible for these moments as well. That main loading is being beared by this main reinforcement. We can have this reinforcement all along our slab section like this. Then we have seen in slabs there is reinforcement like this. We have if you come slab section like this. We have we have one reinforcement like this. I already told you it's responsible for taking bending moment, mu, ultimate moment, mu, responsible for primary. Okay, then we also provide another type of reinforcement about it, that's known as distributive reinforcement. Its diameter is usually less than the main reinforcement. This is distributive reinforcement. secondary or distributed reinforcement. Distributed reinforcement. Its main purpose, like this primary reinforcement, its main purpose is to take the bending moment. Its secondary or distributed reinforcement, its main purpose is to take the stress due to shrinkage and temperature change. Since the depth of our slab systems is very less compared to the beams and columns and other member sections, these slab systems are prone to shrinkage and temperature change very predominantly. That's why to avoid those situations, we provide distributory reinforcement to our slab systems. So there are design rules for this, how much reinforcement you have to provide as primary and how much as this distributory reinforcement. For primary reinforcement, it is governed by MU, how much you will provide MU, how much ultimate moment of resistance or the ultimate moment is coming on your slab system, that will govern how much reinforcement you have to provide. And this distributory reinforcement is governed by how much is the total gross area of your slab system. Gross area of slab system, since we are dealing this slab as a beam of width 1 meter, so gross area will be depth times 1000 mm. It will be gross area, A gross for our slab. So this distributed reinforcement, or we say it EST minimum, it is usually given by as 0.15% or 0.12% of the gross area of the slab AG. And this one is for FE 250 and this one is for FE 415. And this reinforcement governed by moment that's coming on our slab section. And there is another main for this primary reinforcement of the main bars. These phi or the diameter of the main bars. Diameter phi of the main bars should not be greater than d by 8. D by 8. D is the I can see that this is our slab section. I already told you D here denotes the gross depth, and this is by definition 1000 mm. It should not be greater than d by 8, and center to center spacing this much, but it has to be from the center of one reinforcement bar to the center of another reinforcement bar. It should not exceed either 3D or 300 mm. Lesser of the two you have to provide. Now this D here is the effective depth. It will be, we have provided bars here at the slab section like this. It will be bars like this. So our effective depth D. This is for main bars. Why this spacing requirement has been given? It is based on that if we provide our main bars very closer to each other, there we will not be leaving the space for the aggregates to go into the small corners and to every part of the slab. So that when we remove our formwork, there will be a lot of air cavities created in our slab section, or the honeycombing will be formed in our slab section, and we will not allow to do that because that reduces our strength very significantly. This is the main fundamental reason behind it, why we have a limit on the spacing. And same is for limit. The same limit is for the this secondary or distribution reinforcement as well. Their spacing should not exceed 5D or 450 mm. Yes, distributed reinforcement. 5D or for 450 mm. So these are the basic things required for the design of slabs in one direction. So we will begin our problem. There is nothing more required on in this. Yeah, these are the basic things that we require. One more thing, we have this our slab section. I already told you this is the spacing S between the main bars. These are the main bars here. Let me enlarge this section as here, make it clearly, more clearly, because it's 1000 mm. It's very large, a very large width. Compared to our beams, we have 350 mm, 400 mm. We are taking here it as a beam of 1000 mm width. It should be more in this transverse direction. If we take this as our 1000 mm, we have to see the number of bars that we will put place in this 1000 mm. For example, the bars are placed like this: 1, 2, 3, 4, 5, 6, 7. Like these bars are placed like this, and we have I will write it by different color. It is center to center spacing, okay? From the centroid of the steel reinforcement to another steel reinforcement, it is given by S. It is given by small s. So if I will say the area of one bar, cross sectional area of one bar is AB. So I will, and the spacing is S. I will have this is total is 1000. I will have number of bars. Number of bars in 1000 mm will be 1000 divided by S, because spacing is S. So I will have total AST provided in this 1000 mm width will be AST will be N times area of one bar. I already denoted it by area of one bar. N is already here. Plug in it here. It is 1000 divided by S into area of one bar. This is the main thing. Why I told you it here, because in the design process we will require this formula frequently. There you calculate AST. When AST comes out, from AST you have to calculate spacing S. From this formula you directly calculate the spacing as S will be equal to 1000 times area of bar divided by total AST that is required for that 1000 mm width. So remember it to do it like that, because maybe we are confusion in this part. So let's start the design problem. So our problem is like here. We have to design a one-way slab system which has a clear span of 4 meter. I have shown here it a clear span 4 meter. That is the span between the two columns, inner face of the two columns or the inner face of the walls. Clear that is a visible span, and it is simply supported on 230 mm thick masonry wall. Look here, 230 mm. Here it's one wall and it's one wall. These are brick walls. Our slab system is supported on it, and it is subjected to a live load of 4 km per meter square. Live load is acting on this slab system as 4 km per meter square, and it's also having a finish. This finish may be either to the plaster that we apply on it to have the finishes, or it may be the paint or the any other things, or some wood carving done on the slab or the floor system. beneath or above. That is the live load coming from the finishes. That is 1 km per meter square. And the steel that we have to use for this slab section is Fe415, and we have to assume moderate exposure conditions. Exposure conditions are moderate for this structure. So let's start this problem. First, we will assume the effective depth of our slab system. There is a thumb rule for assuming the effective depth. What we do by this thumb rule, we do it by as 1/25th of clear span. This is just first assumption that we do for our effective depth, because later on we will be modifying it as we proceed in our design. D. So effective depth D approximately will be equal to, what is our clear span? Clear span is 4000, and we will have this 25. We are getting a clear span effective depth of 160 mm. So let us keep it for a time being 160 mm. Now we can calculate the gross depth from this clear span, because I will draw. I am having this is my D, this is 1000 mm. So now let's assume this cover for time being to be 40 mm. So we have our gross depth D as D plus cover. When we calculate this, so this is 160 plus I assumed a cover of 40 mm. It gives me 200 mm gross depth of our slab. 200 mm. So we are having approximately, I think, 8 inches of our 8-inch thick slab system. Overall depth or gross depth. So now we have to calculate the effective span of our slab system. Effective span as per code is L effective. We have to take one of these two values. It is effective span is given as, sorry, clear span. L denotes clear span plus effective depth, or it is clear span plus this width of wall, this W, width of supporting walls, either wall, W. When we calculate both these values, we have clear span as 4000 mm plus effective as 160. It is 4.16 meter, and we have 4000 plus 230. It comes out to be 4.23 meter. So we will take lesser of the two. So we will have a effective span as L effective is equal to 4.16 meter. From this effective span, we will be calculating all our quantities required for the design. So effective span comes out to be this. So now we have to calculate span calculation. I will write the steps. Span calculation. First step. So second step is load calculation. Loads coming on our structure, slab system. So distributed live load that is coming from the self weight W, that is dead load, it will be 25 is the from concrete kilometer per meter cube density of concrete multiplied by 0.2, because 0.2 comes from this, it's 200 mm, it will be per meter. Okay, this distributed live load will be coming per meter square area, it will be coming as 5.0 kilometer per meter square. And total dead load, what will be coming as W dead load, let it come delta W due to self-weight, or we can say it as self-weight, will be 5 from self-weight plus 1 from finishing, because it was already mentioned, no? The problem 1 is finishing, it is 6 kilometer per meter square, per meter square. And live load is also coming as a 4 kilometer per meter square. So we have to factor these loads as per code. We have to use factor loads to see the worst combination. Factor loads comes as WU. It is 1.5 times summation of both W live load plus W dead load. This comes when we calculate after plugging all the values. Live load comes to be 4 and dead load comes to be 6. This comes to be 15 kilometer per meter square. Okay. As I already mentioned that this slab system is simply supported. So let me draw the slab system like this. This is simply supported. We are taking this slab system as a beam of 100 mm. So we have a beam like this. Beam system like this. It is simply supported. It is having a total factor load of total factor load of 15 kilonewton per meter square. As it's one-way slab action, it will predominantly bend in this direction. Everyone agrees with this? So we will have a maximum moment at the mid span. So for simply supported case, we will have a mid span mu as ultimate moment coming as W L square by plugging all the values. 15 times here. Keep in mind, every time you use L, it's the effective span. L effective is 4.16 meter divided by 8. You have to be consistent with the units as well. It will come out as 32.4 kilonewton meter per meter. Okay, so this amount of bending moment will be coming on our slab section. And as we have taken the slab section per 1 meter or per 1000 mm, this moment is per 1 meter of the slab section. 32.4 kilonewton meter is coming on each 1 meter of the slab section. This is the moment. For this moment, we have to design our slab section. Now the step is we have to determine our AST. Determining AST, and this AST is for main bars. main bars or primary reinforcement. So for main bars we have to calculate AST. For AST we have the formula like this. AST by BD. From the code we can directly have the formula AST by BD is equal to FCK divided by Fy into 1 minus root of 1 minus 4.598 mU by BD square mU by FCK BD square CK BD square like this. So we have, since we have moderate export jet conditions, we can consider M25 grade of concrete. Consider M25 such that FCK will be equal to 25 megapascal. Okay. So we have the values of all the things. We have MU, FCK, B, D, everything, and FI as well. We can calculate the quantity AST by BD. It is actually AST by BD is the percentage of reinforcement divided by 100. We can write it equivalently as like this. So when we calculate all these things, we get PT by 100 is equal to AST by BD is equal to, we have 25 divided by 2 times 415 because we are using FI 415. 1 minus under root of 1 minus 4.598 into what we are having our values as 32.4 into 10 power 6 Newton meter into mm. Now we are having our FCK as 25, we are having our B as 160, BB as 1000 and D square, D as 160 square. When we calculate all these values, we will get this value equal to 0.734 374 10 to the power minus 2. Okay, so we will have our AST required as AST as per moment requirement will be equal to 0.374 into 10 power minus 2. We will have when we transfer this to this side. Okay, we will get the B is 160 mm. D is D is 160 mm and B is 1000 mm. When we will calculate this, we will get AST required as we will get 599 mm square per meter. Remember the units of this because we are doing every calculation per meter of the beam, per meter of the slab system. So from this we can have to calculate a spacing and the bar that we are choosing. Let's choose. We will choose 10 mm diameter bars. So I already told you from this what you can have. Firstly, we have to calculate A bar. Area of one bar is equal to 5 by 4 d square 10 square. So it will be 78.5 mm square. And AST is already given. So I already told you formula here for the spacing. Spacing is 1000 area of bar divided by AST. So directly we will get the spacing as spacing, area of bar, here we assume spacing will be given as S required. Spacing required will be, it is 1000 times area of bar divided by AST. Plugging all the values, we have 1000, we have area of bar 78.5 mm square divided by, I have 599 mm square. So we will have our spacing as 131 mm. Yes, required will be, it's also required 131 mm, 131 mm. And we will check the maximum spacing limits as well. These are the limits that I already told you. Limit is 3D or 300 mm. Spacing, max spacing. We have to check these limits as well. It is 3D, 3 times 160, it's 480 mm or 300 mm, whichever is less. So our value as per the moment requirement is far below these maximum spacing limits. So we can go with the limit of the spacing given by the moment requirement. So we can even reduce it for and put it as a multiply of 25 for detailing purposes and the other things. We will provide 10 mm dia bars at the rate of 125 mm center to center for main reinforcement. This is the main reinforcement that we have to provide for our slabs. Okay, now we have to go to distribution bars. Now we will go for distribution reinforcement that we have to provide. Main bars we are done, we are distribution bars. So for distribution bars we have to provide these at right angles in the plane to the main reinforcement. Okay, so I told you this distribution bars has to be provided as per the cross section and the grade of the steel of the main reinforcement. Here I wrote this. Yeah, this we have to provide it as a 0.12% of gross area of the cross section. So we will provide it as like this: distribution bars EST. AST distribution. AST distribution will be 0.0012 because it's 0.12% into B is 1000 mm into gross depth D is 200 mm. So we have to provide our distribution bars as 240 mm square. 240 mm square per meter. 240 mm square per meter. So let's assume assuming 8 mm diameter bars. And 5 here I am writing it's the diameter of the bar. Okay, so for 8 mm diameter bar we have to calculate area of bar AB as pi by 4 of 8 square It comes out to be pi by 4 of 8 square, 50.3 mm square. So 50.3 mm square. So spacing required as per the formula already given will be 1000 times area of bar divided by AST. So we will have 1000 times area of bar is 50.3 divided by 240. So S required will be S squared will be 208 mm. So this is the as per the distribution requirement. So we have to look at the maximum space limits given by the code as well. Maximum spacing limits I already mentioned it here. It is either 5D or 450 mm, which is our less. So checking the maximum requirement as well. Max spacing is equal to 5D or 450 mm. 5D is 5 into 160, which is 800 mm. So you are clearly looking as spacing required that we calculated from the distribution requirement is much lesser than the maximum spacing limit. So we can go with our values. So converting it as a multiply of 25, we can reduce it back to 200 mm to be on the safer side. So we can provide 8 fibers at the rate of 200 mm center to center spacing for distribution bars. So our design is complete for 1V slab. We are providing 10 mm diameter bars at 125 mm center to center for main reinforcement, and 8 diameter bars at the rate of 200 mm center to center for transverse reinforcement or distribution reinforcement. For this thing, we have to do the detailing as well, because you cannot provide the design without details. You have calculated all the values, but you have to give it to the engineer. He has to understand it from some drawing. For detailing purposes, you have to detail it very carefully. For that, let's provide this in this way. We have our slab section like this in plan, like this. Okay, we will have the cutting of this slab section like this, because we have to provide that. We have to show where are the these are the walls, masonry walls on which this slab system is simply supported. Okay, we have to give it like this. This is planar. We have to mention the details as well here, like this. This one like this. This was our. Okay, this is like this. This is this. And these are the walls. Every dimension has to be in mm, so this will be 230. Walls are 230, and the clear span between this is 4000, sorry, 4000 mm. This is our walls. So we have to provide main bars. We will provide main bars like this. One bar I will show with different colors. Main bar is okay. This is main bars. Okay, I will provide it like this. This up to this like this. You will have to provide some band to it. I will also give you the reason why we bend this reinforcement towards the wall sections. like this, and we will bend it like this. This is from the pan you are seeing the reinforcement of the main bars. We are providing this band to this reinforcement because you can see that, for example, this is our slab na, this is our beam, this is our beam. At the mid span it is subjected to sacking moment. Here it is sacking moment, so we will provide the bars at the bottom to resist that sacking moment. But then here comes, it is wall, supported on wall. Then if this slab is continuous from this side, at this point the beam is subjected to some hogging movements. To prevent the beam from these hogging movements, we will provide some reinforcement at the top as well, because due to hogging movements the tension will come at the top surface. Instead of placing the bars at the top side, we only bend what we provide the main reinforcement like this, we bend it towards the top when we come to the this to the wall sections. Here I have shown, this is that thing, this is that thing towards the wall. When we move towards the wall, we have bent it like this to turn the main reinforcement to the top side. Here we have again done this. Okay, so we can write this as, we have to write it in where this was our uh, 10 5 bars, 10 mm diameter bars at the rate of 125 mm center to center. Okay, we also provided these distribution reinforcement, distributed bars like this, orthogonal to the main reinforcement like this. So this distribution bars is, we have like this. What are their detailings? These are 8 5 bars at the rate of 200 center to center. This is the main thing. And what we have provided this as, we have used uh, M25 concrete. You will write it like this, M25 concrete. We have used Fe415, and we have provided the gross thickness as D is equal to 100 mm like this. It's the main thing we have provided. Show it like here. Okay, now we have to show it here as well. This one, this main bar, we have to this as distribution bars. Distribution bars. Okay, we have to provide this band at a distance of, I will also write this detail as well. We have to provide this band at a distance of 0.1 L from the face of the wall. This top band, 0.1 L. Okay, 0.1 L. If we draw this section, this was, we have cut this section like this, A. We have taken this section A, this is the A section, like this. We can have same like this one. Here would have been it from the cross section like this. If I cut the slab from the sideways, or you see the cross section how it looked, it would be like this. Sorry, it is here continuous. It is here continuous like this. I will show the reinforcement quickly. Main bar is green color. Main bar is like this. Main bar is like this. Main bar is like this, and here the alternate bars are turned up at some distance 0.1 L. Okay, and we are provided with uh, this distribution reinforcement like this at some spacing. Distribution reinforcement for this bar and distribution reinforcement for this main. Okay, we will have it all over the section like this, and here it's the wall system below it. Sorry, wall system is below it like this. We will have a wall system like this. It is 230 mm, 230, and we provided a gross depth of 200 mm, and we gave this this reinforcement as we gave this reinforcement as 10 bars at the rate of 125 center to center as, and these are alternate bars. Bent up, alternate bars bent up, and we provided these as 85 bars at the rate of 200 center to center as distribution bars. This is 200 center to center, 200 center to center. Here this is again the distribution bars. This is again 85. This is 10.5, 10.5, and we have our effective depth as already this one, 160. Details of one slab that we designed. So you have to do the detailing like this. If you've done the design, after that you have to provide the detailing of the reinforcement and all the dimensions of our slab like this. This completes our section for today, for the week 6, in which we solved a design problem for the one-way action of the slabs. In the coming week, you will be studying the design of two-way slabs in detail, so that in the next week problem solving session we will take the design of two-way slab. We will discuss the problem there one, and starting from basic concepts. So thank you so much everyone for joining today's section. It was all for today. Thank you.